Hello everyone! So we are picking up where we left off in the last video with balancing chemical equations, and we're going to start looking at several examples. Now before we do that, I want to go through some tips that will make balancing chemical equations much easier in your life. The first tip is to identify the most complex substance, and you're going to hear me call this the monster. Okay, so once we've identified that monster in the reaction, we want to choose an element that appears only in one reactant and one product, if possible, and adjust the coefficients to make that element the same number of atoms on either side. Step 3, we are going to balance polyatomic ions. Now I do know that we haven't talked about polyatomic ions, but I will point those out as we go along. One example is NO3, and the way you'll notice a polyatomic ion is that it'll be enclosed in parentheses, okay? So think polyatomic ions, parentheses. And that's not the phases, and I'll show you what I mean when we get to examples. Hello everyone, so we are picking up where we left off in balancing chemical equations, and we're going to run through some examples in this video. And before we do that, I want to go through some tips that will help make balancing chemical equations easier. So the first step is to identify the most complex substance, and you're going to hear me call this the monster. Okay, and then once we identify the monster in that chemical reaction, we're going to choose an element that appears in only one reactant and one product if we can. And we're going to adjust those coefficients in order to get the same number of atoms on both sides. And remember that the only thing you can change in a balanced chemical equation are those coefficients. The next thing we're going to do is balance the polyatomic ions if they are present, and I know we haven't talked about polyatomic ions, but we will see some examples, and you will notice that they're going to be in parentheses. So an example may be NO3, and you'll see it enclosed in parentheses. Okay, step 4, we're going to balance the remaining atoms and usually end with the least complex substance. And hopefully in this course you won't have to deal with fractional coefficients, but there are instructions there if you need them. And then step 5, we're going to count the number of atoms on each kind. We're going to count the number of atoms of each type of element on both sides and make sure that that chemical equation is balanced. And what you're going to find in this process, up in this top corner, we're going to go from reactants to products typically. And you'll notice that I'll start on one side of the reaction, wherever that monster is, and then I'm going to bounce over to the other side, and then I'm going to bounce back and forth. And it's almost like a game of ping pong where I go between the reactants and the products each time that I add a coefficient. Okay? So we're going to go through an example using some of these tips. The first example that we're going to experience is a combustion reaction. And the way that I know that it's a combustion reaction is because of the CO2 and H2O products, as well as that O2 reactant. So what will change is the carbon-hydrogen compound, and it could even be carbon, hydrogen, and oxygen. But all combustion reactions are going to have O2 as a reactant and CO2 and H2O as products. So first, when I notice that it's a combustion reaction, there is a very quick tip to combustion reactions. And that is that you want to balance them in the order of carbon, hydrogen, and then oxygen. Okay? And another reason that you notice that is based off of the tips that we looked at. If you look in step 4, it says to end with the least complex substance. Well, the least complex substance in this case is O2, okay, because it has only one type of element in that reactant. And so I'm going to end with O2, or oxygen. That's the last element that I'm going to try to balance. And so we're going to focus on the carbons and the hydrogens. And for those, it doesn't matter as much which one that you put first. But using the tips that we found, if we identify the monster is going to be the compound that has the largest number of atoms. And in this case, that's going to be your C7H16 because it has the most carbons and hydrogens and different types of atoms. Okay, well, the second tip was to find an element that exists only in one reactant and one product. And that can work for carbon or hydrogen. So carbon only exists in this one reactant, and it only exists in one product, which is CO2. So if we want to balance those carbons, remember, the only thing we can do is add a coefficient in front. And so if we need 7 carbons on the product side to match the 7 carbons on the reactant side, then we add a 7 in front of CO2. And then the next thing that we look at is hydrogen. So for hydrogen, on the reactant side, we have 16 hydrogens. And so we're going to need 16 hydrogens on the product side. Well, remember that I said that your coefficient times your subscript needs to multiply and equal the total number of atoms that you have. So if we place an 8 in front of H2O, you have for hydrogen, 8 is your coefficient, times 2 is your subscript, and 8 times 2 gives you a total of 16. Okay? And we have 16 hydrogens on the reactant side, 16 hydrogens on the product side, so we are balanced for the carbons and the hydrogens. And then if we leave the oxygen for last, we're going to have to add the total number of oxygens that we have on that product side. So if you notice, oxygen exists in 2 products. It exists in the CO2 and the H2O. So if I want to find the total number of oxygens in CO2, that's going to be 7 times 2. So we've got 7 times 2, or 14. And then we have to add to that whatever we have in H2O. And there's no subscript written beside the oxygen, so 8 times 1 is simply 8. And then 14 plus 8 gives us a total of 22. So we have 22 oxygen atoms on the product side, and if we want to make that match on the reactant side, then we're going to need to add a coefficient of 11. And again, if we multiply 11 times the subscript of 2, then oxygen on the reactant side has 11 times 2, or 22. Okay, and now we have all of those elements balanced. So let's run through some more examples. We're going to start out simple and get a little bit more complex. Okay, so from the last video, if you remember, one of the first things I did was I drew an arrow down, or I drew a line underneath the arrow to separate the reactants from the products. And then I listed each type of element that I had. And this is just so that I can look and see how many atoms that I have on each side. So on the reactant side, we're looking at hydrogen, sulfur, and oxygen. And then on the product side, I want to make that match. So we're going to do H, S, and O. Okay, to determine the total number of atoms that I have in a compound, I've got to multiply the coefficient times the subscript. Now, the nice thing is that I don't have any coefficients at the moment, so I can look simply at those subscripts. So H2S, that subscript means that I have 2 hydrogens and 1 sulfur. And then I have a O2, which means I have 2 oxygens. And then on the product side, again, subscript of 2 for that hydrogen. So I have 2 hydrogens and 1 oxygen, and then a subscript of 8 for that sulfur. So from first glance, it looks like the hydrogens are already balanced, and what's not balanced are the sulfurs and the oxygens. So then we look back at the tips, and the first tip was to find the monster. Okay, well, we've technically got 2 monsters here. It's not going to be the O2 or the S8 because there's only one type of element there. We want to look for something that has multiple types of atoms. And so we could either choose the H2S or the H2O. And to keep things simple, we'll pick the H2S since it's the first one that we saw. Okay, then I want to look and see, okay, hydrogen is already balanced. I've got 2 on both sides. So then I'm going to look at the sulfur and see, well, okay, sulfur is not balanced. I've got 1 on the reactant side and 8 on the product side. So if I need to get these to balance, so I need to increase the side that has less, and that's on the reactant side here. I need to make that 1 and 8. And the only thing I can do is multiply by adding a coefficient. Okay, so I'm going to add an 8 in front of H2S. Now, when I do that, I want to go ahead and adjust everything in that compound to see how many that I have of each element now that I've added the 8. So that 8 is going to affect hydrogen. I'm going to have to multiply that subscript of hydrogen 2 times 8. And then sulfur as well. I'm going to have to take that 1 and multiply it by 8. Okay, equals 16 hydrogens now and 8 sulfurs. So the sulfurs are balanced. And then since I affected the hydrogen, okay, since I balanced the sulfurs and I changed that hydrogen, I want to bounce over on the product side and look at the hydrogen on the product side. And if I have 16 hydrogens on the reactant side, then I need 16 hydrogens on the product side. So again, I'm going to have to multiply the coefficient in front of 8 so that I can say 2 times 8 gives me 16. And when I apply the coefficient of 8, it's going to affect both the hydrogen and the oxygen. So I've also got to multiply that oxygen times 8. Now the hydrogens and the sulfurs are balanced, and the last thing is the oxygen. Okay, I have 8 oxygens on the product side and only 2 on the reactant side. So if I want to make the reactant side match the product side, I need something to multiply by 2 to give me 8. And that would be a 4. So that 4 becomes my coefficient, and 4 times 2 gives me 8. And now I have the same number of hydrogen, sulfur, and oxygen on both sides of the reaction. Okay, so my final balanced chemical equation is going to be 8H2S plus 4O2 yields 8H2O plus S8. All right, so I'm going to end this video, and in the next video, I'm going to go through more examples and deal with some of those polyatomic ions as well as another combustion reaction.